So first of all, we will be talking about the order of hyperconjugation. First order conjugation we'll be seeing, and then when we have got second order conjugation, that is the thing what was called as hyperconjugation by Mulliken, my mistake. Then third order hyperconjugation we'll be talking about the same way. Here is the basically idea. What is the first order conjugation? This one, then second order conjugation, and then third order conjugation. First order conjugation is the usual case of conjugation, what we might have seen earlier. This is usual case of conjugation where the electrons from the pi bonds, one of the pi orbitals can be going to another pi orbital. From pi orbital they can be going into p orbital, or non-bonding electron can also be going into p orbital or the pi bond. That kind of conjugations we have seen earlier. That is the case of normal conjugation. In second order conjugation, the conjugation is going to be even weaker, and importantly, the electrons which are being delocalized, they are going to be the sigma electrons. This kind of thing is what we have called as hyperconjugation. Please note, when we have got second order of the conjugation, that is considered as hyperconjugation. So when it will be coming to third order conjugation, that is what we are calling as the second order hyperconjugation. The difference in the usual conjugation what we are seeing and second order hyperconjugation what we are seeing here is, in this case the electrons are being delocalized into sigma star antibonding molecular orbital. Usually when the electrons are being delocalized, they are going either into the empty p orbital, singly occupied p orbital, or empty pi star bonding, anti-bonding molecular orbital, what we say. So these different cases we'll be seeing in our further discussion. I'll be showing one by one what one is the case of the second order hyperconjugation, and in fact we'll be seeing the examples. This one is in the carbocation and free radicals. This one is in the alkenes. These we'll be seeing in different conformers and some other examples. We'll be talking of that in a bit. Then here we have got the thing what we are understanding as second order conjugation. Hyperconjugation we have been actually seeing in the introduction, that here the sigma bonded electrons which are present, those are going to be delocalized into the p orbital or pi star molecular orbital. This kind of conjugation, when sigma bonded electrons are going, they are being delocalized. This is going to be the second order conjugation or hyperconjugation. And this is very much natural that when we have got the electron donor ability and electron acceptor ability, if you have got the electron accepting ability of the empty orbital, if it is going to be greater, then this is going to be much better delocalization. Better the delocalization, greater will be the stabilization for the molecule concerned. Here we are seeing the example of carbocation, where empty orbital is getting the electron from the alpha carbon hydrogen bonds, and this is the case of radical, where this singly like one unpaired electron which is singly occupied orbital is present on this carbon. There we are having the sigma electron being delocalized. These two cases are where we are going to say this is going to sigma to p conjugation. Next case is where sigma bonded electrons are going into the pi star antibonding molecular orbital. That kind of conjugation is also considered as the normal hyperconjugation or the second order conjugation. That's the case what we are considering right now. This is the example. These are the cases when we will be considering this is the second order conjugation. Now, when we say third order conjugation, or when we're talking about the second order hyperconjugation, this is going to be the delocalization into the sigma star molecular orbital. Like this time, this is going to be the acceptor molecular orbital, empty sigma star molecular orbital, when this is going to be the receiving orbital, or this is going to be acceptor, electron acceptor, when this is sigma star. We are considering this is going to be the second order hyperconjugation. And again, that thing is going to be very much Same, better the electron donor ability, electron acceptor ability of the sigma star molecular orbital, better the delocalization would be, and better will be the stability. We have here some example of a molecule where we have got we call the molecule as methyl chloroform. So if you see here, this carbon hydrogen bonds are electron rich, and here there are the electrons present. These sigma bonded electrons can be delocalized, and these electrons can be basically delocalized into this carbon chlorine bond. There will be one sigma antibonding molecular orbital. Along this particular bond, there is going to be one sigma star antibonding molecular orbital. And because carbon chlorine will be having a relatively greater electron withdrawing nature in the carbon chlorine bond, so that just like this bonding molecular orbital electrons are more towards chlorine, the anti-bonding molecular orbital will be having much more tendency to receive the electron. That is what we are saying. The electron acceptor ability of the sigma star molecular orbital is going to be much better over here in the carbon chlorine bond, and carbon hydrogen bond will be having relatively electron donor ability. This one is going to be, the first case is going to be electron donor, this one, and here this one is going to be electron acceptor. So good electron donor, good electron acceptor, this kind of third order conjugation or second order hyperconjugation is going to be possible in this case of methyl chloroform. So the orbital where electrons are going to, that is sigma star, that defines the second order hyperconjugation. We have got one more example of second order hyperconjugation. This is the same example basically we have written with respect to the hyperconjugating structures. So when we are writing basically hyperconjugation, one of the bond is being shifted, we relate these kind of structures as hyperconjugating structures, just as we were talking about the resonating structure when conjugation was there, or sometimes we are calling that as the contributing structures. That should be relatively more correct term. So here what is happening, this molecule is having, CH3 is going to have basically quite a delta positive charge, because those hydrogens are going to be having delta positive spread on this hydrogen, as well as on this. All these three hydrogens are going to have relatively delta positive charge, and all these three chlorines one by one can be having delta negative charge. So the net thing is we can have this whole molecule, this end can be having your positive charge and this end can be having a negative charge. There will be a net dipole moment present along this direction, and this molecule will be having unexpectedly higher value of the dipole moment than what we can think about by the addition of the vectors using carbon hydrogen bond and carbon chlorine bond. Like in any other example, if you have got carbon chlorine bond and carbon hydrogen bond, and if we do the addition, vector addition of those all vectors, this value cannot be justified. We have to take into consideration this kind of second order hyperconjugation, then only we can explain that what we call as unexpectedly higher value of the dipole moment. Okay, I hope you are getting it, that how the hyperconjugation is modifying the property.